We've now trained our first deep neural network for classifying movie reviews by positive or negative sentiment. When we looked at the results, one of the things that we noticed was that maybe the results were a little bit simplistic. The model was looking for single positive or negative words, and we want to create a somewhat more sophisticated model that can take into account, say, pairs of words or triplets of words that convey some positive or negative meaning together. So to do that, you may be surprised to know that you already have the tool in your toolkit that you need. So we're going to use convolutional layers. In the previous live lessons, we used convolutional layers for machine vision to detect features like a particular orientation of an edge wherever it occurs in an image. That was a two-dimensional example, so we had a kind of square scanning the surface of the images looking for those features like edges or whatever in the image. And in these live lessons, our sequence data are linear. The words are just in a single dimension. So our convolution will now be linear in one dimension as well. So some things will be a little bit different, but some things will be the same. The notebook that we're working with is available, already created for you. It's this convolutional sentiment classifier. I'm going to turn off the one that we just created to free up the resources on our machine, particularly free up the resources on the GPU. And so this convolutional sentiment classifier notebook is already ready for you, but we're going to recreate it from this dense classifier demo. So we'll do that by making a copy. The code is pretty similar. We're just changing some of the parameters around. So we're going to call this the convolutional classifier demo. And so we'll change the title appropriately, convolutional sentiment classifier. And we're going to classify IMDb reviews with a convnet, with a convolutional network. Our dependencies are the same as before, except that now we have a few extra layers. So in addition to our dense layers and the related layers, we're also going to have a convolutional layer. It's one-dimensional, as I mentioned, as opposed to the two-dimensional ones we were using for images in the previous live lessons. We're going to be using dropout on those convolutions, as we often do, to avoid overfitting our models. So we'll use spatial dropout one-dimensional. And we will also be using max pooling, which you may remember from our previous live lessons as well. And that's just to reduce the dimensionality of the problem. I'll explain that in a bit more detail when we get to building our architecture. I'm going to restart and clear the output on this kernel so that we have a blank slate to work with here. All right, let's load our dependencies. We're going to set a new output directory name here. I'm going to call it conv. We're still going to have 4 epochs. Our batch size will still be 128. Number of dimensions in our vector space embedding can stay the same. So I'll leave most of our vector space and embedding parameters the same, except with this more efficient convolutional layer, we can increase our maximum review length from 100 to 400 without losing much speed on our training time. And we're also going to add dropout into our embedding layer. That's something new that we hadn't been doing before. We're going to randomly drop out 20% of the neurons in the embedding layer, another scheme to avoid overfitting. And we are going to decide on our convolutional network architecture. We're also going to have a dense layer after our convolutional layer. It's going to have more neurons in it. So let's have 256. We will decrease our dropout a bit. Now that we have dropout in our embedding layer as well, let's try reducing our dropout to 0.2. It's a hyperparameter you're very welcome to play around with. And we also need to decide on our convolutional layer hyperparameters. So let's have 256 filters or kernels or neurons in that convolutional layer. And we also need to decide on the size of our kernel or our filter. Recall that with the MNIST digits, when we were looking at images, these were squares, so they could have been 2 by 2 or 3 by 3 or 4 by 4 squares or whatever. We're only going to have one dimensional on our sequential natural language data now. So let's set it to 3. So we're looking for sequences of 3 words in a row that convey positive or negative sentiment. That's what our model is going to be looking for. All right, and we're going to load our data. This time, I'm going to digress away from the way that Moss and his colleagues in their 2011 paper set these things up when they were getting these IMDb data together. I found empirical playing around with this that leaving those most common words in improved the fit of the network. So let's remove that parameter, load in the data. And we no longer need to be looking at the data. We did that sufficiently in the previous notebook. We also don't need to restore the words from index. We did that more than enough earlier. So let's just pre-process our data. There we go. And we don't need to look at these cells anymore. Design our neural network architecture. We do need to make some changes here. So our embedding layer stays the same, except that now we're adding in dropout to our embedding layer as well. To do that, we're using the spatial dropout 1D layer, which is designed for this kind of situation. And we're dropping out 0.2, 20% of the neurons on every step. As our next layer, we are adding in a convolutional layer. We actually don't need the flatten then anymore. We needed that as an interim between the embedding and the dense to get the dimensions of our matrices to line up properly. But with this convolutional layer going in, that'll handle itself. So let's add in a convolutional layer, one-dimensional one, and we're going to have the 256 filters or kernels that we decided on. It's going to be of length 3 for the filter and the kernels, and as is often the case for our hidden layers in the middle of our network, we're going to be using ReLU activation. Cool. And what should we pass this convolutional layer into? Well, we're going to pass it into a max pooling layer. So we're going to use a max pooling layer again. We did that very frequently in the previous live lessons with our MNIST digits and our image data. That was to reduce the dimensionality then, and it's the same here. A difference is that in the max pooling that we were using in our image, in our MNIST digit classification, we set a specific kernel size. So we might say on a given 2 by 2 square, we're going to take the most activated value from that 2 by 2 and have just that single value go forward. We specified the kernel there. In this instance, we're going to use a parameter called global max pooling, which just takes however many values are available to it, which will be 3 in this instance because that's the size of the kernel that we decided on with our k_conv parameter. And it is the case that in natural language processing, we typically use this global max pooling as opposed to the filter-based one. Because we are using it globally, we don't need to specify a specific max pooling kernel dimension. And our dense layer, we're going to leave that the same. Our dropout layer, we're going to leave the same. Our output layer, we're going to leave the same. Cool. Let's have a look at that model. It is looking good. So you can see now that we actually have fewer parameters. We had 700,000 in our dense or fully connected network that we based this notebook on, and this network only has 400,000. So that's because of the efficiency of the convolutional layers. They're doing some more advanced calculations than just a dense or fully connected layer. Our model compile is going to be the same. Our model checkpoint is also going to be the same. I'm just going to move all of these into a single cell. And then we're going to train our model. And there's nothing different about our model training. This line also stays the same. It'll take a few moments to train. Because our parameters are pretty small, we don't have that many. We just have to wait for the data to be put on a GPU. So we can actually watch that happen. So you can head in to your terminal, and if you type in NVIDIA SMI, you can have a look in real time at the data being loaded in. I'll do that again later when it takes a little bit longer. So you can see because we were loading onto the GPU, if you're not using a GPU at home, if you're just using the CPUs, then you won't have this step. It means that we spent 30 seconds, or about 27 seconds, of this first epoch loading information onto the GPU so that we could then do the training in the subsequent epochs much more quickly. That kind of trade-off ends up being more valuable when you have models that take longer to train. In the end, how did we perform here? So in the second epoch, that's our best performing epoch. It has our lowest validation loss, and it has our highest validation accuracy. So that's cool. So we'll continue to work with that epoch and have a look at the results. This is quite a bit better. In our dense classifier, we had results of, our very best result was 84.7% classified correctly. Now we're getting 89% classified correctly. That's a big jump. So switching to this convolutional architecture seemed to be a good idea. Now let's load the model weights from that second epoch. Because we're zero indexing, that's 0.01. And let's have a look. Let's calculate our y-hats, our predicted values for our validation data. We don't need to look at that anymore. We can look at a plot of the results. So now, compared to our dense results, the decisions should be slightly stronger. So it has, as you can see, if the convolutional network has more of the reviews as predicted to be very positive. So the negative reviews are about the same height at the most extreme level. This is about 8,000 reviews in that lowest bucket in both notebooks. But at the high level, we went from having less than 7,000 that the model was very confident about to well more than 8,000, pushing 9,000 in that top bucket. So we have a more opinionated model, and let's see if that bears out in better results on our AUC curve, and indeed they are. So we were covering 93% of the area under the curve with our dense classifier. In our convolutional classifier, we're covering even more, 96% of the area under the curve. It's a really good classifier. So we don't need the rest of the lines in this notebook here. So we can tidy things up. Excellent. That's it. We've built a really solid convolutional classifier. We've been using primarily the layers and the techniques that we knew from our previous live lessons. The only thing that we've added in so far that's new is this idea of vector space embedding and using one-dimensional convolutions as opposed to two-dimensional. Coming up next, we're going to be using some types of neurons that are specialized to working with one-dimensional sequence data like natural language. Let's see how they perform.